So last time we went through the oxidative phase pathway, starting with glucose 6-phosphate and ending at ribulose 5-phosphate or ribose 5-phosphate, however you want to think of it, and generating 2 molecules of NADPH. And I think I left it with this question of, which gets at sort of the biological function of the pentose phosphate pathway. So I said ways that cells can use the pathway. Use is a very good word. So one way is to, if the cell needs to make NADPH and ribose 5-phosphate, then it does the oxidative phase of the pathway, starting with glucose 6-phosphate, and that's pretty straightforward. But the second issue is if the cell doesn't need ribose 5-phosphate, if the cell needs NADPH, but it doesn't need ribose 5-phosphate, then the cell can do the oxidative phase up till ribose 5-phosphate or ribulose 5-phosphate, and then go back to glucose 6-phosphate by the non-oxidative phase, followed by several steps from gluconeogenesis. So this is what I wanted to discuss. So I sort of sketched this out last time that, or at least mentioned it, that let's think of it as starting from ribulose 5-phosphate. And what I think I said is that the non-oxidative phase of the pentose phosphate pathway, you could say it starts here, and it ends with 2 molecules of fructose 6-phosphate plus glycerolate 3-phosphate. And so these are one way to think of the end point of the non-oxidative phase. And so then I pointed out that 2 fructose 6-phosphates, that's 12 carbons, and glycerolate 3-phosphate is 3 more, so it's 15 carbons there, and there's only 5 here. So the way that to make all this balance, not that the cell necessarily is counting molecules, but if you want to write it and have the stoichiometry work out, then you'd have to say, take 3 of these, and that's enough carbons. That's 15 carbons, and that's enough carbons to make the 2 fructose 6-phosphates and the glycerolate 3-phosphate. All right, so that's I think the non-oxidative phase. So in the book, they show the non-oxidative phase going all the way up to glucose 6-phosphate, at least in this figure. But here's a more detailed figure that shows it a little bit better. Right? So in the upper left, they've got ribose 5-phosphate. I added ribulose 5-phosphate just so we don't forget about it. Okay? So this is a complicated series of reactions. In the past, sometimes I would go through them step by step and expect people to know, but I'm not going to do that. All right? So you don't have to know these reactions. Let me just say a little bit about some of them. So let's see. First of all, I said up here on the board that we're going to start with 3 molecules of this. That's 15 carbons. So you could say we're going to start with 3 molecules of ribulose 5-phosphate, which is there. This pointer works great when I point to the floor. But, or you could say that you're starting with 3 5-carbon molecules, and you could, if you want to, you could say that those 3 are ribose. 1 are ribose 5-phosphate, and 2 molecules of xylulose 5-phosphate. So what's xylulose? I'm sure everyone remembers. It's D-xylulose. D-xylulose is made by this enzyme called epimerase, which makes epimers. So if you remember what an epimer is, an epimer is a sugar that differs from this one at only the stereochemistry of only 1 carbon. It can't be this one because they all have to be D. So that helps me know that xylulose is this. If this is Fisher projections. Okay, so there is an enzyme that will reversibly convert ribulose 5-phosphate to xylulose 5-phosphate. And so it's actually the two xyluloses. Note that there's a xylulose in the lower right. You could say it's the two xyluloses plus the ribose that are this, what we need for this pathway. However you want to think of it. All right. So let's start up here in the upper left with a ribose plus a xylulose. Right? So that's 10 carbons, two 5-carbon molecules. And this enzyme called transketolase, whose mechanism I won't discuss. I just want to point out, it's kind of interesting, is what this enzyme does is it takes these two 5-carbon molecules, and you see it makes glycerolate 3-phosphate, which is 3. So it's going to take 2 of the carbons, I think, from the xylulose, and it's going to give them to the ribose, and that leaves 3, which is G3P. So that's 3 carbons. So that means that the other product is 7 carbons. And so I just want to point out that the product up here, there we go, is cetoheptulose 7-phosphate. So that's a 7-carbon sugar. It's a ketose. That's the only 7-carbon sugar that I know of that has any significance in metabolism or biology. So I just want to bring that to your attention, that that's its claim to fame, is that it's an intermediate in this pathway, not anywhere else. Okay? But it's an intermediate. It's formed by this enzyme called transketolase, but then it's immediately used in the next step by this enzyme called transalylase. So transalylase is sort of like aldolase in that it takes this cetoheptulose, it does an aldol cleavage reaction, but then unlike aldolase, which is done once it's done the cleavage, it first does a cleavage and then it does an aldol condensation. Right? So the net result is that it's going to take cetoheptulose, which is 7 carbons, and it's going to take 4 of those carbons and make erythrose 4-phosphate. Right? So there's erythrose. That's a 4-carbon sugar. It's an aldose. And so that's the only place that I'm aware of that erythrose has any significance in biology. Okay, so let's see. There were 7 carbons plus 3. We split off 4. That leaves how many? 6. And that's enough to make a fructose 6-phosphate. Right, so it's all the carbons are accounted for. Okay? All right, so that's the 6-carbon product. Note that this G3P is not a product because it's made but then used up. So that's not the G3P, but note that there's another G3P, glycerolate 3-phosphate, in the very lower right. And that comes from taking erythrose 4-phosphate plus another xylulose, that's 9 carbons, and again, transalylase. Transalylase is going to take 2 carbons from here, that leaves 3, that's the G3P. And it's going to take 2 carbons from this molecule and give them to the erythrose, and that's going to give us the other fructose 6-phosphate. So 3 carbons, 6 carbons, and all the carbons are counted. So it's really just these 2 enzymes. And the chemistry is actually, well, transalylase basically does what aldolase does. So the reaction is something we've always seen. Transketolase is different. We haven't covered anything like that. Okay. So this is the sequence of reactions can occur. So again, for the stoichiometry to make everything add up, you have to start with 3 5-carbons and make the 2 6-carbons and a 3-carbon. Okay, so these reactions are all reversible also in the cell. Okay, now, so what we thinking about, the issue was that the cell needs to be able to make NADPH, but not ribose. Instead, once the ribulose 5-phosphate is made, I said the cell is going to just make it back into glucose or glucose 6-phosphate. So glucose 6-phosphate goes to ribulose 5-phosphate, we lose 1 carbon, which goes to the 2 fructose 6-phosphates plus the G3P. And now, if you do gluconeogenesis, we know how you can make glucose out of these things. Okay? So you can get back to glucose 6-phosphate, I think most commonly, perhaps at liver, you might make glucose out of it. So that just sort of finishes that question, or addresses that question. Yes?
Could you alternatively use these products to glucolysis?
Yeah, so that's actually the third way. So this sort of is a little bit more complete picture of what I just said. So we started with glucose 6-phosphate here in the right. We did the oxidative phase. We made the 2 NADPHs and 1 carbon, right? So we're going to count carbons more completely in a minute. So there's one of the carbons. We made these 5 carbon guys, and then we made them back into these products. And then now on this figure, you know, they just remind us of the enzymes that you need to get from these products in red up back to glucose 6-phosphate. Okay? So that's, again, the second thing the cell can do. Let's just think about what, go back to overall stoichiometries. So last time, they gave us stoichiometry. Well, you could say, start with glucose 6-phosphate, one of them, and to make ribulose, 5-phosphate, you lose one carbon as CO2. But now we're saying we want to start at glucose 6-phosphate, and we want to be able to get back to glucose 6-phosphate. Okay? So what we said is, to get back to continue here, we need to take 3 of those and make these into 2 molecules of fructose 6-phosphate plus a G3P. Right? So now, how can we get from here back to here? All right, well, so first of all, let's see. If we're going to make 3 of these, that means we need to start with 3 of these, right, which means we're going to make 3 CO2s. We have 2 fructose 6-phosphates. We can just make those back into 2 glucose 6-phosphates directly. But G3P, there's only 3 carbons. So we need 3 more carbons. We have to multiply everything by 2. So we need to make 4 fructose 6-phosphates. That's enough to make 4 glucose 6-phosphates. But by multiplying everything by 2, I'm going to get another one of these. Right? And that's enough to make 1 more glucose 6-phosphate. Right? So now to make everything sort of balance and everything add up, you have to say we're going to start with 6 glucose 6-phosphates. We're going to make 6 CO2s. And then we're going to have all of these are intermediates. And we're going to end up with, we're going to regenerate only 5 glucose 6-phosphates. Okay. So we started with 6 glucose 6-phosphates, and we get 5 of them back. But the other ones, the one that we don't get back is in the form of CO2. What's the net reaction? We started with 6 glucose 6-phosphates, but we made 5 of them back, so that leaves 1 that went away. So the net reaction is 6 glucose 6-phosphates. I didn't put in the NADPHs, but we need 12 NADPP plus. All right, and so what happens to this? It's now 6 CO2s. So the net reaction in doing this in the cyclic form is to take one glucose 6-phosphate, oxidize it completely to 6 CO2s, and generate 12 NADPHs. And you might need 12 protons to make everything balance. Right? And so, you can think of it that way. This is how the cell can just generate a lot of NADPH without making anything else. Note that 12 NADPHs, each NADPH has 2 electrons, so this is 24 electrons. Right, so to oxidize glucose all the way to 6 CO2s, you get 24 electrons out of that. In this case, that's what we do. All right, so that's how that addresses that second way of using this pathway. The third way, actually, is what was coming from the question was asked a few minutes ago, is this is something that probably happens in the liver, perhaps other tissues, but I don't know. But consider you've just eaten a big meal, right? So you're well fed. That's what well fed means in this context. You just ate a huge meal, tons of carbohydrates. And so under these circumstances, one of the things that your liver will do is your liver makes fatty acids, which are used to convert to fat, and you store some of that, all that food that you ate, you store it as fat. So the liver is going to want to make fatty acids under these circumstances. So to make fatty acids, we'll do the pathway later, but to make fatty acids, you need acetyl-CoA. That's where the carbon atoms come from, so that's 2 carbons each. And so there's a pathway to get from there to fatty acids. You need some ATP, and you need NADPH. So what the liver can do is it can take glucose 6-phosphate, and it can do glycolysis. And to make pyruvate, and then as I've said, the pyruvate can be converted to acetyl-CoA. So, that's how you can, the carbons in the glucose, 4 out of 6 end up here. Right? So you need carbon atoms, right? You need ATP, well, you get some ATP out of this. And then for NADPH, what the liver will do is it will take some of the glucose 6-phosphate and it will do the oxidative and non-oxidative phases to make fructose 6-phosphate plus glycerol 3-phosphate, meanwhile generating NADPH. Right? So it'll take some of the glucose and use it to generate NADPH, because that provides NADPH, right? Right now, these things, of course, are intermediates of glycolysis, and so under these circumstances, rather than using them to regenerate glucose or glucose 6-phosphate, they could continue in glycolysis. And so this is, I would say, this is a third way, that this pathway can be sort of integrated in metabolism. It's not shown explicitly on the slide, and I might have added that arrow, but these things could go up, but they could also go down in glycolysis towards pyruvate. So that's the third way that the cell could use this pathway, is to generate NADPH, but then otherwise continue in glycolysis. And so that means do the oxidative phase, the non-oxidative phase, and then take those products and just let them go back into glycolysis. So that's the third way. And then there's a fourth way that, at least in principle, a cell should be able to use this pathway. And that is, what if the cell doesn't really need any DPH, but it needs 5-ribose 5-phosphate? Right? So the way to do this is to do the non-oxidative phase but going backwards, because the reactions are reversible. Right? And so I guess the way to do this might be to start with glucose and do a little bit of glycolysis, and then these products, fructose 6-phosphate, glycerolate 3-phosphate, can the figure all the arrows are going from right to left, but the arrows can also go from, no, they all go from left to right. The arrows can all go from right to left. So the glycerolate 3-phosphate, fructose 6-phosphates, they can be used to make ribulose 5-phosphate and ribulose 5-phosphate. So this would be a fourth kind of way that this pathway can be used. Are there any questions? Okay, so the last aspect of carbohydrate metabolism I want to discuss is glycogen, which I guess is introduced in chapter 14, but then is covered, I think maybe in more detail in chapter 15 in the context of regulation. And I'm going to discuss the regulation of this pathway in this time a little bit. I just want to go through the chemistry of it to start with. So, let me complete the glucose part of this figure. So there's the pentose phosphate pathway branching off from glucose 6-phosphate. Glucose 6-phosphate, as I've said, is also a starting point to make glycogen, and glycogen can be broken down to form glucose 6-phosphate. So So glycogen, remember, is a polymer of glucose. Glycogen is made and it's stored in cells, and it's made mostly in muscle cells and liver cells. Both of these cells, it's used as a way to sort of store essentially glucose, but the metabolism of these cells is different. So let me just comment on kind of why these cells want to have glycogen. So let's consider a muscle cell, and so this is a cell membrane, and this is the blood. And when you're well fed, so you just ate a big meal, ate a lot of carbohydrate, your blood glucose levels go up. And so it's under those circumstances that glucose that's in the blood gets taken up into the muscle cell. And there's a transport protein I'll say a little bit about probably next time. But there's a transport protein that enables the glucose into the cell. So now what is a muscle cell going to do? So you just ate a big meal. You don't really feel like doing anything because you ate so much, you just want to go to sleep. So you lie down in front of the TV set. And so you're not going to really, you don't need any ATP, right? So what are you going to do all those glucose? Well, what you're going to do is make glucose 6-phosphate, which happens right away, of course, hexokinase. And then the glucose 6-phosphate will be used to, will be incorporated into a glycogen chain, right? So, in other words, the glucose has been stored in the form of glycogen. Right? Later on, the glycogen can be broken down again, or, well, the glucose can be removed from the glycogen and come off in the form of glucose 6-phosphate. What is a muscle cell now going to do with the glucose 6-phosphate? Well, the only thing a muscle cell is going to do with glucose 6-phosphate is glycolysis. And so that it can make ATP. And then what happens after that depends on, the circumstances, right? But so the glycogen is a reserve supply of glucose so that the muscle cell can generate energy when it needs to. When you're exercising, when you're being chased by a tiger. And so that's what it's for. Let's contrast that to a liver cell. So the liver cell cell membrane, glucose in the blood. So again, if you're well fed, the liver will also take up glucose, and it can enter the liver cell, and it can be made into glucose 6-phosphate, and then again that can be added to a glycogen chain. Again, it's a way of storing glucose for later on. So in the case of the liver, though, what the liver is storing the glucose for is later on, after you've eaten, 12 hours later, your blood glucose levels are falling. The liver needs to make glucose to put back into the blood. So in the liver, glucose residues can be broken off glycogen in the form of glucose 6-phosphate. Remember, the liver has this enzyme glucose 6-phosphatase. And that's the enzyme that enables the liver, and only the liver, to make glucose from glucose 6-phosphate. And the transporter can allow the glucose to go back out of the cell. Right? And so this is a really important function of the liver, is to generate glucose that gets transported out of the cell, and then the brain uses it mostly. And so that's a slightly different function of the liver than the muscle. So the liver will do this. The liver has a certain amount of glycogen. It'll break down the glycogen. And I think by the morning, it's broken down essentially all of its glycogen. So in the morning, apparently what the liver will do also is it will take various things, lactate that other cells have made, maybe some amino acids, make oxaloacetate out of that. It'll do, even after you've eaten, the liver will do gluconeogenesis.